Hello students, today's topic is dielectrics. Dielectrics are non-conducting substances. This will not allow the flow of charges through it, but these substances can permit these charges to exert electrostatic forces on one another through it. This dielectric is essentially an insulator. It can be polarized through small localized displacements of its charges. Examples: glass, wax, water, air, wood, etc. Molecules of a substance may be of two types, polar or non-polar. Based on that, here we can say two types of dielectrics there: polar dielectrics and non-polar dielectrics. Polar dielectrics: a molecule in which the center of mass of positive charges does not coincide with center of mass of negative charge, then we can call that as a polar molecule. Dielectrics made of polar molecules are called polar dielectrics. Example: water, HCl, CO. Non-polar dielectrics: a molecule in which the center of mass of positive charges coincide with the center of mass of negative charges. They are called non-polar molecules. Dielectrics made of these non-polar molecules are called non-polar dielectrics. Example: hydrogen, nitrogen, oxygen, carbon dioxide. Polarization of a non-polar dielectric in an external field. Here you can see the figure in absence of electric field and in presence of electric field. In the absence of electric field, you can see in figure the centers of positive and negative charges of the molecules coincide. The dipole moment of each molecule is zero there. But in presence of an external electric field, you can see their centers of positive charges are displaced in the direction of external field, but the centers of negative charges are displaced in the opposite direction of electric field. The displacement of these charges stops when force exerted on them by the external field is balanced by the restoring force due to the internal field in the molecule. This induces dipole moment in each molecule. That is, each non-polar molecule becomes an induced dipole. The induced dipole moments of different molecules add up, giving a net dipole moment to the dielectric in the direction of external field that you can see in the figure. Polarization of polar dielectric in an external field. Polar dielectric, you know, the centers are separated by a distance there. The molecules of polar dielectric have permanent dipole moments. In the absence of external electric field, these dipole moments of different molecules are randomly oriented due to thermal agitation in the material as shown in this figure. So we can say there the total dipole moment is zero. But when an external field is applied, that time the dipole moments of different molecules tend to align with the field. Due to this, there is a net dipole moment in the direction of the field. The extent of polarization depends on relative values of two opposing energies. These energies are potential energy and thermal energy. Potential energy means potential energy of the dipole in the field. That tends to align the dipole with the field. Second one, thermal energy of agitation, which tends to randomize the alignment of the dipole. So from this we can conclude polar and non-polar dielectrics develop a net dipole moment in the presence of an external electric field. This is known as polarization of the dielectric. What is polarization? Polarization is defined as the dipole moment per unit volume. Its magnitude is referred as polarization density. Direction of this polarization is same as that of the external field. The polarization of dielectrics reduces the electric field inside the dielectric. Let us see how. For that, we have to consider a rectangular dielectric slab placed in a uniform electric field acting parallel to two of its faces as shown in the figure. Its molecular dipole aligns themselves in the direction of electric field. That is the reason for uniform polarization of the dielectric. That means every small volume of the slab has a dipole moment in the direction of electric field. Positive charges of the dipoles of first vertical column cancel the negative charges of the dipoles of the second column. Like that way, that will happen. Thus, the volume charge density in the interior of the slab became 0. However, there is a net uncancelled negative charge on left face, like that positive charge on right face of the slab. Thus, the polarized dielectric is equivalent to two charged surfaces with induced charge density. Induced surface charge density that we can take as plus or minus sigma p. These induced surface charges set up an electric field. That means the field due to polarization inside the dielectric, its direction is opposite to that of the external field E0. This tends to reduce the original field in that dielectric. So we can say the resultant field E in the dielectric will be that external field minus polarized electric field. E0 minus EP and directed in the direction of external field, that is along E0. If we take the ratio of the original field and the reduced field in the dielectric, that we can call as dielectric constant or relative permittivity. Thus, we can say K or epsilon R is equal to that external field by that reduced field E0 by E0 minus EP. Polarization density. Induced dipole moment developed per unit volume of the dielectric when placed in an external electric field is called polarization density, denoted by the letter P. Let A be the surface area, D be the thickness, and plus or minus sigma P we can take as the surface charge density, plus or minus QP be the charge on the surfaces. Then we can say sigma P is equal to QP by A. Then P is equal to polarization density is equal to dipole moment by volume, QP into D by A into D is equal to QP by A, that is equal to sigma P. Electric susceptibility. If the field E is not large, then polarization P proportional to resultant field E existing in the dielectric. P proportional to E, that we can write P is equal to epsilon 0 chi E. Here chi is the proportionality constant called electric susceptibility. From this we can write chi is equal to P by epsilon 0 E. Thus, the ratio of polarization to epsilon 0 times the electric field is called electric susceptibility of the dielectric. The dielectrics with constant chi are called linear dielectrics. Relation between dielectric constant and electric susceptibility. You know E is equal to E0 minus EP. EP is equal to sigma P by epsilon 0 equal to P by epsilon 0. From this we can write E is equal to E0 minus P by epsilon 0. Then E is equal to E0 minus, instead of P we can write epsilon 0 chi E. Then E is equal to E0 minus epsilon 0 chi E by epsilon 0. We can cancel epsilon 0. Then we have to divide both sides by E. Then we will get 1 minus E0 by E minus chi. E0 by E you know, that is K, dielectric constant. So 1 is equal to K minus chi. From this we can write K is equal to 1 plus chi. Dielectric strength. The maximum electric field that can exist in a dielectric without causing the breakdown of its insulating property is called dielectric strength of the material. Its unit is volt per meter. Thank you.